once again welcome students for the second session on logarithms in the IIT PAL lecture series. I am Neelesh Upadhye from IIT Madras. So, in this session what we will do is we will make few quick observations about the properties about the definition of logarithms, and from that we will derive some properties of logarithms. Then we will really study properties of logarithms which are laws of logarithms, which will be helpful in solving problems, solving many problems in fact for the day to day purposes, and it will give you a hold on any problem consisting of logarithms, and we will solve elementary problems based on our knowledge about the laws of logarithms. This is what we will do in today's class. So, let us start. Let me briefly summarize some observations and properties. I am reiterating these properties because they are very helpful in calculating many of the logarithms or solving many problems related to logarithm. So, this you know, log to the base a of a is equal to 1. Let me quickly derive it. How to derive this? This is let us say log to the base a of a is equal to x. This implies, I will apply the 7th rule, it means a raised to 1 is equal to a, but this a means it is a raised to this means a raised to x is equal to a, this means a raised to 1, which implies x must be equal to 1. Okay. The next property is, just I am using log to the base 1 by a of a, this I am saying is equal to minus 1. How to derive? Again it is very simple, it is log to the base 1 by a of a is equal to x. 7th rule implies 1 by a raised to x is equal to a, that means a raised to minus x is equal to a raised to 1, that means x is equal to minus 1. Okay. Next property, log to the base a of 1, any base a of 1 is equal to 0. How to prove this? Again log to the base a of 1 is equal to x, say, then a raised to x is equal to 1, but 1 is nothing but a raised to 0, this forces x to be equal to 0. Okay. And the last property, which I am again repeating because this is very crucial in solving the problems, is equal to b. I do not need to prove this because I have already proved it. Okay. Then in the next session we will see some problems. So, in today's class we are going to study laws of logarithm. Sometimes these laws are called properties of logarithms. For this we will assume certain things. So, let us assume some conditions on the base and some conditions on the numbers or the arguments that we give in log. So, assume a is greater than 0. In general a will be our base, a is not equal to 1, m and n are positive real numbers that we will assume to be greater than 0, and we need one more condition, c to be greater than 0 and c not equal to 1. Okay. With these conditions I will in today's class I will prove the following properties. First property is log to the base a of m into n is equal to log. This property helps us to simplify the calculations, mainly whenever you come across a complicated multiplication and you apply a log function, then you can split the product into the sum of two logs. Okay. So, this is one property. Similarly, there will be a property for division, that is log to the base a of m divided by n is equal to log to the base a of m minus log to the base a of n. So, these properties have special names, I will write the names after once I have finished writing these properties. Another property is log to the base a of m is equal to log to the base c of m upon log to the base c of a. This is notice here what I have done is we have changed the base of the logarithm. C is any other base of the logarithm, and it should, if c is the base, it should satisfy these conditions. C should be greater than 0, c not equal to 1. That is why we are putting these two conditions. Next property is, again you can see this as a corollary of the first property, but still we will enlist it separately. Log to the base a of m raised to n is equal to n times log to the base a of m. So, let us come to the names of these properties. The first property in logarithms is called multiplication law. This is multiplication law. Then what will this be, what can this be called? This is division law or quotient law. Let me write quotient law. Some people call this as addition rule of log, the first property, and the other rule as subtraction rule of log. So, you should also keep that in mind. Then this property is called change of base property. As this property allows us to change the base of the logarithms, right. So, this is a change of base property, and naturally this property, because I am dealing with exponents, it is exponent law or power law. Let us call power law. So, all these properties we will try to prove in this class, and we will give some limited examples of these properties to understand. So, let us first prove the first property. We will use the red color, and so let us write proofs. I will extensively use my 7 rule which I discussed in the first class to prove these properties. So, first is our multiplication law. So, multiplication law says that if I am taking log to the base a of product of two numbers m into n, this is equal to log to the base a of m plus log to the base a of n. How will I prove this? I have already given you some hint that I will use my 7 rule extensively. So, we will try to use our 7 rule extensively. Let me choose the blue color. In order to use 7 rule, anything that comes with log on the right hand side I will write is equal to x say or y say. So, log to the base a of m is equal to x say. Similarly, I have the expression I will write on the right hand side, log to the base a of n is equal to y say. Now, if I want to prove this property, I have to apply the 7 rule. So, I will draw a 7 across this. So, this is my 7 rule, which means my a raised to x is equal to m. If I apply 7 rule across this, then it is a raised to y is equal to n. By this time you should be familiar with this 7 rule, and it should be your second nature. So, if a raised to x is equal to m, a raised to y is equal to n, look at the LHS which we want to prove, log to the base a of mn. So, it is natural to take the product of m and n. So, if I take the product m n, what will it be equal to? According to this, m is nothing but a raised to x, n is nothing but a raised to y. So, it is a raised to x into a raised to y. I will use the law of indices and say that this is equal to a raised to x plus y. Okay. So, what I got is m into n is equal to a raised to x plus y. Now, this is the exponent form of the expression. If I want to convert this expression into log, what will I get? My a is base. So, base will remain base. So, when I write logarithm, log, base will be the base, this number will come on the left hand side, which is m into n, and this is equal to x plus y. But what was our assumption? What was our x and what was our y? So, this is equal to log, I am substituting the value of x which we have assumed, to the base a of m plus log to the base a of n. Okay. See, we have proved whatever we were supposed to prove. So, what we have proved right now is log to the base a of m into n is equal to log to the base a of m plus log to the base a of n. So, how this property can be used? Suppose I have been given log to the base a of 12, okay. Then I can rewrite this as log to the base a of 4 into 3, which essentially means it is log to the base a of 4 plus log to the base a of 3. Right. So, this is the simplest demonstration of the property of logs. Okay. Now, this property, let us remark something. This property can be extended to any finite products. For example, let me write that property. If I have log to the base a of m n p q, what will be the result? It should be log to the base a of m plus log to the base a of n plus log to the base a of p plus log to the base a of q, right. This should be clear. If you want to derive it in the manner I derived, you can actually use the above property and say that this is in fact equal to, so let us try to derive it in a way we derived, m n p q. You can split this into two parts, one part is mn, the other part is pq. So, I can rewrite this as log to the base a of mn plus log to the base a of pq. Okay. If this is clear, then again on this product I will apply my first property and I will get these two terms. Sorry, okay. I will apply this thing and I will get first these two terms, okay. And I will apply again the same property, multiplication law, on the next two terms and I will get this term. Okay. So, we have derived that you can actually extend this to any finite product. Okay. Let us now go and prove the second property. Second property was division rule or the quotient rule. So, let me change the color. The color was red when I derived. Okay. So, the second property is division rule or quotient rule. We have called it as quotient law. So, quotient, what is a quotient law? It is log to the base a of m divided by n or m upon n is equal to log to the base a of m minus log to the base a of n. This should be straightforward. Now, again I am using 7 rule and I will rewrite these expressions in the exponential form. So, let me change the color. I have chosen orange last time. So, I will rewrite this as log to the base a of m is equal to x. See, again I am repeating the steps, so I will be little bit faster. See, I will use the 7 rule on both expressions, and then it will be a raised to x is equal to m and a raised to y is equal to n. If a raised to x is equal to m and a raised to y is equal to n, then I am interested in this kind of expression. So, I will write m upon n, which is equal to a raised to x upon a raised to y. So, by using law of indices, it will be a raised to x minus y, because a raised this is well known. Anyway, I will list it. A raised to x upon a raised to y is equal to a raised to x into 1 upon a raised to y. In last class, when we solved the example, we have proved that it is a raised to x into a raised to minus y, which is equal to a raised to x minus y. Okay. So, now what we got is m by n is equal to a raised to x minus y. Okay. And therefore, m by n equal to a raised to x minus y can be written, if I take the log on both sides or I convert this form to exponential form, it will become log, conversion of this to exponential form, it will become log to the base a of this number, which is m upon n. This also we have seen earlier, is equal to x minus y. We also know log x is log to the base a of m, y is log to the base a of n. So, this will be log to the base a of m minus log to the base a of n. This proves the second property. A natural extension of this property, will be, I can write this as, I will use the green ink, log to the base a of m upon n upon p upon q. What will this be equal to? This should be equal to log to the base a of m. I will use the quotient rule, which is minus log to the base a of n p q, which is also equal to log to the base a of m minus log, then I will use the product rule here, to the base a of n minus log to the base a of p minus log to the base a of q. So, this is in this corollary is in combination with product rule and the quotient rule. So, you should remember this helps a lot in simplifying the expressions containing log. Okay. So, let us go ahead and try to resolve the problem of change of base. So, let me derive the third property, which is change of base property. Okay. Before that, I have not given any example for this. You can actually cook up some example. Say for example, log to the base a can be any base, upon 3 upon say 15, but it is completely divisible. So, 15 into say 4. Okay. So, what will this be? This is equal to, this can be written as log to the base a of 3 minus log to the base a of 15 minus log to the base a of 4. Okay. So, this is the use, I have demonstrated the use of this property. Now, let us take the third property, which is change of base property. this can be quite helpful when you have some complicated bases or you have to change the base of something, some log. So, change of base property says that if I have log to the base a of m is equal to, then I can change the base of this logarithm to c by using this manipulation. Okay. So, this is the change of base property. In order to prove this property, I will slightly rearrange the property saying log, this is equivalent to log to the base a of m into log to the base c of a is equal to log to the base c of m. Now, you notice the relation, a here is in the base, here a is in the argument. So, I want to use this argument, but as usual most of the properties can be proved using 7 rule. So, I will try to use 7 rule and I will give some nomenclature like log. Okay, I have in earlier cases I have changed the color. So, let me change the color so that I am precise in saying that I am proving. Let us take the orange color. So, let us take log to the base a of m is equal to x, say. Another thing, log to the base a, sorry, now I do not have any base a. So, I have log to the base c of a is equal to y, say. And the third one was log to the base c of m is equal to z. Now, I have to exploit the relationship between a in the base and a in the argument. Okay. So, that is what I will do now. So, now this simply means a raised to x is equal to m. I am using 7 rule, I am converting c raised to y is equal to a, then c raised to z is equal to m. Okay. So, these are the 3 conversions, but notice here this a and this a is because of the base, this a is because of the argument, right. So, I can substitute a is equal to c raised to y in this expression. Let us see what I get if I substitute this. So, c raised to y the whole raised to x is equal to m. Okay. But my m from this expression is nothing but c raised to z. Okay. If this is the case, then what I am essentially saying is, using laws of exponent, c raised to xy is equal to c raised to z. What does that mean? That means xy is equal to z. Why? Because if I say log to the base a of x, let me not give the x. So, log to the base a of m is equal to, again I am using m. So, let me not use m. So, let us say some number L, or let us say some number r is equal to log to the base a of s, then I know this forces me, because we have studied in properties of exponential function and logarithmic function, they are one to one. So, this forces me to say that this is equivalent to saying r is equal to s when they are in their valid domains. Okay, this if and only if r is equal to s. So, I have used this property and said that this implies xy is equal to z. Now, let us go back and see what is xy. x is, I am substituting from here, x is log to the base a of m. Let us give brackets, so that then log to the base c of a, which is also equal to, according to this expression, log to the base c of m, isn't it? That means what? That means I have proved whatever I am supposed to prove. Right. So, this is a change of base theorem, which is very helpful while deriving certain properties. So, so if you rewrite this, you will get this property. So, we have proved this property also. Now, let me give one demonstration of this. So, suppose I have a log of some x and a, okay. So, and I want to change the base, right, but I want this base to be a, so that I will not get this number. Okay. Then what I will do is, instead of c, I will put the instead of c in this formula, I will put c to be equal to a in this formula. So, in this formula I will put c to be equal to a, then what I will get is log to the base a of a upon log of x to the base a. So, this is nothing but 1 upon log to the base a of x. Oh, but this is a new property, right. So, if you want to change the base, and if you want to make the base to be the argument and argument to be the base, then what you have is a new property, which is, let me change the color, use this color, let us see how it looks. Log to the base x of a is equal to 1 upon log to the base a of x. So, change of base in action is this, right. So, I have changed the base to the argument and argument to the base, okay, provided they satisfy all properties. So, but both of them are non-negative. Only problem comes when you have 1 here. So, if a is equal to 1, you are in trouble. Why? Because log to the base x of 1 is equal to 1 of, according to our formula, log to the base 1 of x. So, this is a problem, right, because this particular thing is not defined. So, you have to always remember in mind while changing the bases, that if you are coming across such a base which is 1, then the log function is not defined. So, you have to be little bit careful while deriving these properties. Now, let us come to the last property that we are supposed to derive, which is the fourth property, and it is called power law. So, let us see what power law gives us, and it can be seen as corollary of multiplication rule, but that is only for integers. So, here we are deriving in more generality. So, it is the fourth property is called power law, and this property can be written as log to the base a of m raised to n is equal to n times log to the base a of m. Okay. How to prove this property? Again, we will use a standard technique, which is a 7 rule, and we will try to derive this property. So, what we will do is, we will put let me choose the orange color, because in this lecture I have chosen orange color when I am deriving the proofs. So, I will again write log to the base a of m is equal to x, say. Similarly, here I have m raised to n, so I will use a to the base log of m raised to n to base a is equal to, say, y. If I say this, then using 7 rule, I know a raised to x is equal to m, a raised to y is equal to m raised to n. Now what I will do, if I call this equation as star and if I call this equation as double star, then I will use the value of m in star and put that value in double star to get a raised to y is equal to a raised to x the whole raised to n. So putting the value of m in from star to double star, I get this expression. So according to law of indices, which I have repeated very frequently, this is nothing but a raised to nx. If this is a raised to nx, a raised to y is equal to a raised to nx, I know that exponential functions are well defined and they are 1 1 and on 2 on the respective domains. So I also know that y must be equal to nx. But what is y? I will substitute the value of y from our first assumption, namely these two. So what is y? Y is log to the base a of m raised to n, which is equal to n times log to the base a of n. This proves our power law, which is what we are supposed to prove. Now let me take some 1 minute, it should be, sorry, I made a mistake, it should be m. Okay. Another thing is, I will give you one nice demonstration of this. We have been using this. See, when we are asked to find log to the base 2 of 4, what we have done? We have actually used a 7 rule and we have written this 2 raised to x is equal to 4, and then by inspection we guessed that that x should be equal to 2. Instead of that, you can actually write log to the base 2 of 2 square. This is in the argument, this is in the base. So if this is in the base, then I can using this property, I can easily write this to be equal to 2 times log to the base 2 of 2. The property that we proved in the earlier lecture, that is log to the base a of a is equal to 1. We can use that property and say that this value is 2. So this is our demonstration of power law. So we were using power law without actually knowing the power law in earlier examples. We have seen many properties of logarithms. Let us now start solving some problems on logarithms. So here is a first problem, which is simplify. So you will be given a complicated expression and you have to simplify the expression to 1 log. So the expression over here is 1 upon 2 log to the base 5 of 36 plus 2 log to the base 5 of 7 minus half log to the base 5 of 12. First, if you want to apply any law of logarithm, check for the base. So here all the bases are 5. So you can apply multiplication rule in this case. But the problem now is these numbers half, 2, half, these numbers will not allow you to apply multiplication rule directly. So what rule you should apply first? First, you need to understand that because there is a number, you need to get the rule which has a number in front of the logarithm. So let me choose some other color. Let us take a brown color now. So log to the base of a, let me rewrite this. So you have seen one rule, which is log to the base a of m raised to n is equal to n log to the base of a of m. I will use this rule first. Okay. What is this rule called? Power law, which was the last entry. So, if I want to use my power law, this will be equal to log to the base 5 of 36 raised to half plus log to the base 5 of 7 square minus log to the base 5 of 12 raised to half. So, I have used only the power law. Now, I can use the multiplication rule as well as the division rule together, that is multiplication law and division law or quotient law, as I mentioned earlier, quotient law. These two laws will yield. Before doing that, what is the square root of 36? 36 is a perfect square. So, this will be log to the base 5, the first number. Since I am using the multiplication rule, I will write a big bracket, and then what should be the first number? Since 36 is a perfect square, square root of 36 will be 6. Then 7 square, you know what is 7 square? 7 square is 49 into 49, right? And because this is a minus sign, I will get this number, which is root 12 in the denominator, but I can simplify root 12 because root 12 is 4 into 3, square root of that. So, square root of 4 is 2 into root 3. Okay. So, what will this number be? If I want to simplify further, this 2 gets cancelled with 2 of this 2 gets cancelled with giving 3 in the numerator for because of 6. So, log of 5, this is 3, and if the 2 3s are 6, and now root 3 is there. So, this will yield root 3 and 49 will be as it is. So, it is 49 square root of 3. Okay. So, this is a demonstration of 3 rules, in fact: power law, multiplication law and quotient law. Okay. So, we will now take a next example. Let us say second example. Let us take a green color. Second example. Second example says evaluate and naturally it will be a complicated quantity with log in the expression, log to the base 5 of 4th root, 4 is inside the square root sign, 4 is inside the root sign, 25 upon 625. So, generally whenever the question of evaluate comes, you need to simplify the log and give a number as a answer. So, let us see what can you do with this. Again, if you look at this expression simply, what are the you have to think about what are the rules of log that you can use for solving this problem. So, what are the rules of log that you can use? So, let us analyze the terms. Let us do some rough work here. So, 25, 4th root of 25 means 25 raised to 1 by 4. So, definitely if I have expression of this form, I will need power law. Okay. Then I have numerator upon denominator. So, what is the thing that I need? I need multiplication. I do not need multiplication as such, I need a quotient law. So, and I think these two laws will suffice, and some properties of log that we have studied. that also will suffice. So, let us try to solve this problem now. So, first log to the base 5 using quotient law will be 25 raised to 1 by 4, right, minus log of 5 to the base 625. So, this is a use of quotient law. This is equal to log to the base a of m raised to n is n times log to the base a of m. I am using that rule, which is my power law. (625). Now, here are two ways to handle this. You can because my base is 5 and 25 is divisible by 5 and 625 is also divisible by 5. The question that I can ask is, can I write 25 is equal to 5 raised to x, which is our 7th rule. Now this should be your second nature and you should say that yes, we can write, or else if you can write this in a form of power law, that is 5 base 5 square minus log to the base 5. See, now you notice 25 square is 625. So, if 25 is 5 square, 625 will be 5 raised to 4. If you write this in this form, if you write this expression in this form, then again I can use my power law and say that this is equal to 2 upon 4 log of 5 to the base 5 minus 4 log of 5 to the base 5. So, this is in fact equal to 2 by 4 minus 4 into log of 5 to the base 5. Now, you know log of a to the base a is equal to 1. Right. So, this quantity will be 2 by 4 minus 4 into 1. So, you can easily evaluate this quantity and it should turn out to be 16 of 2 minus 16, which is minus 14 upon 4, which is nothing but minus 7 upon 2. This should be the answer to this question. So, you just review the steps. What are the laws of logarithms that we have used? We have used only power law and quotient law. Where did we use power law? To simplify this term, we have used a power law. Then you can actually solve this by using a 7th rule, but instead of using a 7th rule, what we did is we used again power law and said that this is 5 square, this is 5 raised to 4. Therefore, power law yields 2 log to the base 5 of 5 and 4 log to the base 5 of 5, right. And then we use the property log to the base 5 of 5 is equal to 1. Okay. So, this is what the summary of what methods we have used to evaluate this expression. Now, I will give a very complicated expression which we have to evaluate. So, it will be slightly tricky, but you can do it. So, let us use the blue ink. So, this is the third problem. This is a third practice problem that we can solve. So, again the question is evaluate now. You note down the question very carefully. If you make some mistake in noting one of the numbers, then you may get a wrong answer. So, it is 16 times log to the base 10 16 upon 15 plus 12 log to the base 10 of 25 by 24 plus 7 log to the base 10 of 81 80. This is a problem. How we will solve this problem? Again, evaluate means I will find one number. Okay. How will you solve this problem? And first we have to review what are the rules that I can use for solving this problem. So let me take this. Okay. So what are the rules I can use? Do I have any numbers in front of log? Yes, I have. I have many numbers in front of log. So I have to use which rule? Power rule. I have to use power law to simplify. Then I can use quotient law because I have fractions of this form. So I have to use quotient law. What else I can use? Because there are many pluses, there are many additions, so I have to use the multiplication rule also. So I have to use all these laws and I have to simplify this expression. So let us go step by step. Log to the base 10 of 2 will be as it is. Log to the base 10 of 2 will be as it is, plus log to the base 10. I will use a power law and pull the 16 as a multiplier to the power. So 16 by 15 raised to 16 plus log to the base 10 of 25 by 24 raised to 12 plus log to the base 10 of 81 by 80 raised to the power 7. Okay. Now I am in a position to apply. Now I am in a position to apply the multiplication rule. So I will simply take all the terms together and see if something simplifies. Right. So it is log to the base 10 of. So I am using a multiplication rule. So 2 into 16 upon 15 raised to 16 into 25 by 24 raised to 12 into 81 by 80 raised to 7. Okay. Now, do I need to use a quotient rule? Here the quotient rule may not help. If these terms 15, 24 and 80 I can express in as multiples of 2, 3 and 5, which I feel I can do in this case. Okay. So let us try to do that. So this is log to the base 10 of, what is 16 in terms of 2? It is 2 raised to 4. So 2 into 2 raised to 4 the whole raised to 16. What is 25? I am just taking the numerator, and similar things I will do for denominator. 25 is nothing but 5 square raised to 12 into 81 I know is 9 square, and that also means it is 3 raised to 4. So it is 3 raised to 4 into 7 upon, what is the denominator? I have 15. 15 can be seen as 3 into 5. So I will write separately 3 raised to 16 into 5 raised to 16 into 24 is 8 into 3, but 8 into 3 can also be seen as 2 raised to 3 into 3. So I will get 3 raised to 12 into 2 raised to 3 into 12 raised to 12, 3 raised to 12 into 2 raised to 3 into 12 into 2 raised to 3 into 7 into 10 raised to 7, 2 raised to 3 raised to 7, yes, okay, into 10 raised to 7. But this also can be further simplified as 2 raised to 7 into 5 raised to 7. So, this I will rewrite as 2 raised to 7 into 5 raised to 7, which again means it is 2 raised to 4 into 5 raised to 7. So, I will just merge it here, 2 raised to 4 into 5 raised to 7. So, I will cut this out and this is into 5 raised to 7. Okay. Now, let us tally the indices using laws of indices. So, here it has nothing to do with log now, it is just a minor multiplication question. So, it is 2 into 16 4s are 64 into 5 raised to 24 into 3 raised to 28 upon 3 raised to 16 into 3 raised to 12. So, 3 raised to 16 plus 12, which is 28, 3 raised to 28 into 5 raised to 16 into 5 raised to 7, which is 16 plus 7. So, 5 raised to 23 into 2 raised to 36 and plus 2 into 2 raised to 28. So, it is 2 raised to 36 plus 28, 36 plus 28. Okay. Now, let us try to simplify. So, this 36 plus 28 sum up to 64. Then I think we have done a nice job, and 2 raised to 64 cancels with this 2 raised to 64, 3 raised to 28 cancel with this 3 raised to 28, 5 raised to 23 and 5 raised to 24 will get cancelled and will yield log to the base 10 of 2 into 5. So, it reduced to a very simple number, that is log to the base 10 of 10. Do we know what is this log? Log to the base a of a is always 1. Okay. So, we have solved this complicated problem now. So, to summarize today's lecture, what we did is we first made few quick observations based on logarithms definition, then we derived the laws of logarithms, and then we have solved roughly around 3 problems demonstrating the properties of logarithm and how to use the properties of logarithm to solve the problems. Namely, we have solved the problems of the form of evaluate. Okay. So, in the next lecture what we will do is we will more rigorously use the properties of logarithms. Here in today's lecture I have not used few properties like change of base property, which we will use in the next class. So, wait and watch. I hope you had an interesting session today. So, in the next class we will meet once again and we will solve some elementary problems on logarithms and demonstrate the usage of properties of logarithms. Thank you for watching.